Swayam Prabha. Digital India. Educated India.
So we will continue with our morning agenda. So this is the second half of this talk on generative adversarial networks. So in the first part, just quickly to recall, what we covered is the definition of min-max point, the definition of max-min point and saddle points. What is the connection between these three, right? And just to summarize, the min-max point, min-max value, so for any given function, min-max value and max-min value always exist. Saddle point may not even exist, but if min-max is equal to max-min value, then saddle point will be always existing, and which is essentially the same. Min-max point is same as saddle point, as same as max-min point, and the value is also same actually. So that's all, right? And then we studied von Neumann's theorem, which says that for what kind of functions there is a guarantee that saddle point will exist, right? So if function is continuous in each of the variable x and y respectively, right? And if it is convex in x and concave in y, then always min-max value of the function will be equal to max-min value, and therefore saddle point will exist actually. So with all this paraphernalia, now we are switching the gear. As I told you in the morning, we will be talking about what is generative adversarial network, and they are very, impactful ideas in the parlance of deep learning, and have made a profound impact on the literature. So let's start with that. So first I will start with what is called generative models, okay? What is generative model? So before we get into all these details, I know that many of you have no prior background either in machine learning or deep learning. So I'll start with a very simple analogy, right? All of you know the probability theory, correct? And I think all of you have heard the word statistics. So in a layman's language, I say that statistics is inverse of probability theory. What does it mean? That probability theory kind of give you a mathematical framework to define or kind of build the model of uncertainty, right? So you define, let's say this is the distribution, that is the distribution, Gaussian is a distribution, exponential distributions and blah blah and all that, right? That's a modeling framework actually. Now at a very coarse level, statistics can be viewed as a inverse of it, in the sense that their data is given to you by sampling from some distribution, right? And you do not know the distribution. But your problem is reverse, that given the data, you are supposed to find a distribution which might be generating this data, or some IID samples are given to you. Making sense? So for example, there is a bias coin or a bias dice, let us say. I roll the dice or flip the coin, but I don't tell you how much bias is there in that coin or in the dice. And then I give you the outcomes of that, random experiment. After I flip the coin or roll the dice, I just give you the outcomes, readings. Then I ask you that, can you guess what is the probability distribution of the bias coin? What is the probability of head and what is the probability of tail? It might not be half and half. It is probably a bias coin, or might be half and half. I am telling you nothing. You just have to, by looking at the sequence of head, tail, head, tail, head, tail, your goal is to guess that distribution, right? It's a very simplistic scenario. But imagine that data is coming from high dimensional space. For example, I may even define a valid probability distribution on XY plane, where I pick the points with some probability, right? So you know the Gaussian distribution, the normal distribution. The normal distribution is a distribution on real line. One can also define two-dimensional Gaussian, where the XY pairs are getting picked with certain probability distribution. Now imagine that I don't tell you what is the probability distribution with which I am picking these XY pairs, but I give you XY pairs which were sampled by some distribution, and your problem is to guess the distribution. This is typically one of the central problem in statistics and machine learning, right? Given the data, you try to infer the distribution. Now what happens is so this is what this picture depicts, that suppose there is a some distribution D which sample the data from some domain X, okay? So this X denotes, it could be some Euclidean space, it could be Rn, let us say. So these X's are being sampled from some Euclidean space as per this distribution PD of X, and if you see that I have put inside some cloud, which means you can't see it, it is hidden somewhere actually, okay? But what is given to you is this IID n IID sample from this distribution x1 to xn. Fair enough? Now, what is a generative model? So, if somebody gives me this sample data, there are two routes actually. In one route, I may ask you to guess this distribution, right? Suppose your guess distribution is PG of x. We call this PG of x is the, the model distribution. See, PG of x need not be same as PD of x because nobody knows what is PD of x, right? What we know, God only knows what is PD of x. What they have given to me is the sampled data from the distribution, completely unknown distribution. You will never get to touch, feel and see it actually. You can only see it via these samples actually, right? So no way, even if you come up with a very good guess, still you can never be 100% sure that this is indeed identical distribution to this, right? You can only hope so, all right? So in generative model, there are two branches. In one branch, our goal is to spit out, this is a machine, this is some model, mathematical model or algorithm you can call it, which takes input this n number of samples and it outputs a probability distribution over this data space. Hopefully, this distribution is same as this unknown distribution. So the algorithm is typically designed in such a manner that you spit out a distribution which you believe will be very close to the true distribution, right? These are called explicit generative models. So these are all generative models actually, right? Because here you are talking about the generation process of the data. By what process the data were generated, you are trying to, infer that process actually, right? Data were generated by this process of this probability distribution and you are trying to infer that. In one case, it is explicit inference. In another case, this is called implicit models. What is implicit model? In implicit model, you don't care for the probability distribution. What you say, I don't care what is the distribution hidden in the cloud from which data is being generated. That is not my problem. Even if you don't give me the distribution, you give me a capability by which I can draw yet another sample from the same distribution. Even if my access to the cloud is stopped, let us say, still just by looking at n number of samples, can I gather enough information about this distribution such that I can generate yet another sample xn plus 1th sample. This xn plus 1th and xn plus 2th sample identically, they are not very truly coming from PD of x, but hope is that as if these are coming from PD of x actually, right? These are called implicit generative models. Is it clear? Am I making sense? So suppose there is a bias coin and I am flipping the coin and I flipped n number of times and you have made the note down observation head, tail, that sequence you noted down. One question could be, I ask you that by looking at this sequence of head and tail, tell me what is the probability of head coming of the coin which I was tossing, from which I generated this data. I could have asked you that question. Another question I could have asked you is, okay, you don't tell me what is the probability, but tell me if I flip it one more time, n plus 1 at time, what do you think will be the outcome? Give me remaining sequence. You get my point? So suppose I had sampled it 2n number of times, but I revealed only n outcomes to you, and I have hidden the remaining n plus 1 at 2n outcomes with me. I am not telling you that. And I am asking you that given this partial sequence, can you guess the remaining sequence? See, if you can guess the probability distribution right, obviously you can solve this another problem, right? Suppose if you can get the explicit estimation, this PG of x is my estimation of the distribution, and PD of x is ideal distribution, which I will never come to know. I will hope that this is close to this actually, and there are some statistical ways to measure that closeness actually, okay? If you can do a good job here, obviously then you can generate this sequence, right? Why? How? If you know this distribution, then you just start sampling the data from this distribution. If I tell you that what is the bias in the hidden coin, if somehow somebody comes and whispers you in your ear that whatever coin he is tossing with, the head probability is this much. Suppose somebody whispers this statement in your ears, then what is there? Then you don't have to worry, then you can sample n plus 1, n plus 2 or whatever it is, right? Take some coin with the same bias amount and keep sampling. So, if you know the explicit model, you can generate this sequence, that's not a problem. So, in general, this is a harder problem than this problem, okay? But many times what happens is, and in fact before GAN came, most of the literature was heavily focused on this explicit model, where they used to start with family of distribution and try to find in this space of the probability distribution which is the best fit distribution with the underlying this unknown distribution, and used to pick that and output that actually. Most of the existing, prior to GAN, although it's not that there were lots of work in this direction also, but GAN purely focuses on this kind of approach, where, so in some sense generative adversarial networks are, you can think of their implicit generative models, but they do fantastic job in terms of generating this sequence. And why they are successful? Because they are not going this tough route of first finding out the probability distribution and then using that distribution to generate the sample. They short circuit this journey because this is a harder problem. Is it making sense? Because I am asking everything. But then the question is everything needed? Because if your end goal is to generate few extra sample from the same distribution, if you can do it without even knowing the complete information, then why should I not solve the simpler problem, right? And that's where the winning power of GAN comes. So let's move and I'll show you. So what does it mean? So this is the taxonomy of generative model, and I have taken from, this famous book on deep learning by Aaron Corville, Ian Goodfellow and Yoshua Bengio, published in 2015. Okay. So these generative models, this is the broader class of models in deep learning and machine learning, which deals with modeling the generative process of the data. They can be divided into two categories, explicit density and implicit density, as we saw in the previous slide. Then this explicit density again has the several branches. One is called tractable density, another is called approximate density, and in approximate density again you have the variational methods and Markov chain based methods, right? Like Boltzmann machine and variational autoencoder. If you have heard of some of these terms, they fall in this variety actually, but I am not going to go into detail of any of them. Our focus, today's focus, is more on this branch actually, implicit density. In implicit density, again there are two branches. One is called Markov chain based, okay, another is called direct method, and that is what is GAN. So there are some other methods also which are Markov chain based, like GSN, generative stochastic networks and all, whose principle is little different actually. They operate on the principle of Markov chain, but then GAN is quite effective actually, and they have been very successful. So we will spend time and energy on talking about this branch, only this leaf node. Anything else I am not going to touch upon in this today's talk. But still it's important for you to know the whole landscape, that where do we stand. So I am talking about generative models, which is a very important sub branch of machine learning and deep learning. Okay, and by and large, in a very layman's language, I can say the goal of a generative model is to try to model the generation process of the data, right? Or try to model the probability distribution which led to the generation of data which I am being given or I am seeing them, right? And then there are various ways to go about it, and we will be focusing on this implicit way, where I will not bother about learning the density explicitly, but I will able to learn some model which will give me, if I ask, it will give me one more sample, as if that sample is coming from the same distribution. With me? Okay. Let's go next. So this we talk, right? So why GAN became so popular? So what happens is in the machine learning community, in deep learning community, okay, any kind of data, whether it is the image, whether it is the text, or whether it is numbers, they assume that these data are coming from some probability distribution. For example, images. What is image? On digital computer, an image is nothing but a matrix actually, right? With some value of the pixels, right? So that can be viewed as if I unfold it row wise, I can consider it as a very long gigantic vector. That's all. So it's if it is a 70 cross 70 image, it's as long as it's like 70 cross 70 size long vector actually. It's lying in some Euclidean space. That's all. So every image, mathematically you can visualize in your mind, assuming it's a one channel image, black and white image, because typically we have 3 channel RGB channel for images on digital computer. So you have it's more like model as a tensor. But let's not worry, suppose you have only one channel image, black and white image. So where this image, for example, can be viewed as a long vector, as simple as this. Is it clear? But now what happens is this, you can imagine if it is a 74 cross 74 pixel, this dimension will be almost 5000 r power 5000. It's such a huge dimension actually, right? It's a very big space. If you imagine, the three-dimensional space itself is like anant, right? I mean, it's like infinite. So you can imagine r power 5000 space, how much volume it has, right, actually. So the thing is that, but not every point is a meaningful image. That's the point. Any meaningful image which you see, this is a very sparse space. Only very few points are meaningful images. Any other point, if you take and you print it on computer, it will seem like some garbage actually, right? It's some scribbling, some junk actually, meaningless. So the important point is, because R 500 dimensional space, R 5000 dimensional space is so huge space. Imagine that this room actually, this is like R3. I'm just as a miniature model I am saying actually. Only few points, each point here is a one dot, right? Which is, let's say, R 5000 or whatever, it corresponds to some image. You can convert it into an image, right? But only few of the points, very small subset of this whole space is a meaningful images, and you want to know which is that portion, right? So think of that when we focus on these handwritten digit images. Let us say these handwritten digit images you can view as a probability distribution in this whole room, that the digit 9 is concentrated on a very small region, digit 1 is concentrated on a very small region, right, as a probability function. And you can think of like these handwritten digit images of 1, 2, 3. There is a variation from one person to another person, right? How you write these digits variations, but by and large they are nothing but you can think of them as some random draw of some sample. You are sampling these images from some distribution in this very high dimensional space. Is it making sense? So what this generative model do, once you have done this kind of a modeling that images are coming as sample points from very high dimensional vector spaces, then if I give you these sample 9, 3, 9, 3, 9, these are like 4 samples I have given you, right? Random sample, you can think of that. Then what I am trying to do, I am interested in generating yet another sample as if that sample is coming from same random distribution, right? That's what GAN do actually, generative adversarial network, right? Okay, but they operate on such a high dimensional spaces actually, okay? Now same thing was, so this was the idea proposed by Goodfellow in 2014 in NIFS paper, and this paper has accumulated almost 10,000 citation if you go and check within the span of 5 years actually, right? Which is like remarkable achievement. And then this is another paper roughly at the same time, and these are the images they worked on, colored images, generation of colored images. This was more simplistic exercise because they were trying to learn the distribution, probability distribution with which images are sampled from these high dimensional spaces, but this distribution is relatively simpler. But this distribution is much more complex, right? So what happens in machine learning and deep learning, everything is a probability distribution. All the data we assume, the handwritten digits images or even the pictures, whatever pictures you take, the assumption is that if it is a picture of bedrooms, all the pictures of the bedroom in this universe, if you put them together, you can visualize for modeling purposes that as if they are coming, they are sampled from some proper probability distribution over the space of all images, where the probability mass is concentrated on some region, which corresponds to mostly the bedroom images, let us say, right? Because I told you that R power, any image of 74 cross 74 pixel, you can generate infinitely many images, right, with 74 cross 74 pixel, am I right? So which means this unfolding this vector, there are infinitely many possible images. So if you are interested in bedroom images, that has to be really narrow region in that large volume. How do you learn that probability mass, that which region the probability mass is concentrated? That's the challenge actually. Are you getting the feel for the, before I get into more fancier maths, the concept is important, basics, right? Okay? All right. So, okay, so just I wanted to highlight this one interesting blog by Avinash Hindupur, and this picture I have taken from same blog, and then credit goes to Bruno. What this picture shows, and on the right hand side this shows, is that since the invent of GAN, there are so many variants of this GAN has come up, and that is what we call as GAN Jew. It's like a Jew. You take a keyword and put it, you will pretty much find that GAN, like F GAN, fair GAN, U GAN, doubly GAN, truckloads of different GANs ideas have been proposed, right? For different setting, by changing this setting, that setting. But the mother of all this invention is original GAN generative adversarial network, right? And this is kind of a growth on the literature on this topic, right? You just count the number of papers having this title, in their title the word GAN or generative adversarial network, and you can see how the volume is rapidly building. It's like exponential growth in the research community, right? This is how it has picked up actually, but it has merit, and you will see how cute the idea is. All right, so here is the gentleman, Ian Goodfellow, and who is the inventor of this idea among other colleagues. So this is the paper, Ian Goodfellow and Jean and blah blah, and the last author, Yoshua Bengio, he was his PhD advisor, okay. So this appeared in NIFS 2014, and this is the idea. So idea is this, how does it work? So suppose you have n number of samples given of some images, let us say like these are the handwritten digit images, x1, x2, xn, there are n number of images which are given to you, suppose. So this we call as a data, the original data D which were sampled from PD, okay. Now in this architecture there are two devices, two boxes, one is called generator, another is called discriminator. This discriminator is also known as critique or adversary. So if you go to control theory community, they call this as a critique, okay. If you go to some branches of machine learning, they call it as adversary. Some people call them as a discriminator, but doesn't matter. I will tell you what is the idea. So the idea is this, okay. Before I tell you this idea, let me just tell you one simple thought process which kind of goes behind this idea. So suppose x is some random variable, okay, and px of x, this is the probability distribution of this random variable. I hope all of you know what is random variable, what is the probability distribution of a random variable, right? Now suppose I define, so let's say this could be simple Gaussian distribution, doesn't matter, some probability distribution. Now I define another quantity y which is some function of f of x. For example, it could be, let us say, x cube minus x square plus 5x power 1/3. Just giving some random function, doesn't matter actually. So it is some function. What does it mean? I can sample some value of x from this distribution. So let us say I generate the data from this distribution. So let's say my data is nothing but x1, x2, xn. I generate n sample from this distribution. With each sample I plug it into this equation, and I will get, so let's call the d of x, I will get this sample of d of y, y1, y2, yn, right? Where what is the relationship between each yi and xi? So yi is equal to f of xi, am I right? Now x is a random variable. If you just focus on these values of y, they will also sound as if they are, this is some random variable. Y is also a random variable, right? But what will be the probability distribution of y? It will be some probability distribution which will get decided by two things. One is what is this probability distribution and what is this function. These two things together will dictate what is the distribution of y. So this data, even though I am generating x, from x I am producing y, but automatically it will induce a distribution on y. Does it make sense? So the pipeline is this. So you have this distribution called px of x. This distribution, you are sampling these samples x1, x2, xn. Think of this more like a flipping a coin actually, or rolling a dice, doesn't matter, right? Then all of this data you are feeding into this function f, and what you get from this function is this sample y1, y2, yn. Am I right? You can keep on going infinitely. If I put this whole machine as a black box, one box, this whole machine I can think of it as if it's a sampling machine. It is sampling me the values of y, right? Now if I talk about, so this must be some distribution, it's just that I don't tell you the explicit distribution. So let's say that the distribution is py of y. Now this py of y depends on what thing? It depends on two things. One is what is this function, because if I change this, for the same sample x, output will change. Am I right? If I change f, that same sample x1 to xn, these values will change. Second thing, if I change this distribution and keep this fixed, these numbers will change and therefore they will change. So it depends on two things. One is this, one is this. Both these two boxes define this distribution py of y. So this is called, you are inducing a probability distribution on y via some other distribution. I started with a random variable x and took a function, transformed that distribution into this distribution on y. Is it making sense? So in some sense, pictorially you can say there are two spaces, x space and y space. Okay, there is this function f, and if I have some over this space, I have some distribution px of x, then it will induce a distribution called py of y. So this is called induced distribution. Okay, fair enough. Now why am I talking all this? So let's go back to this picture. So suppose your problem is that you wanted to induce a distribution on this images space. Now think of your y as nothing but a space of images, right? This x1, x2, xn, makes sense? From which images are coming, and you don't know what is that distribution is. So what you did, you start with some simple distribution. Let's say this z1, z2, z, this we call as a noise actually. You start with some simple, univariate Gaussian distribution, you take samples actually. Then this green box here, this is analogous to this function f which I mentioned there, right? This is called data generator. So you pass this noise to this function called data generator, which essentially does nothing but transforming this one-dimensional quantity to this long vector, which is your image. Some function, right? How does it matter actually? You give me a function and I can transform it into, by choosing an appropriate function, I can transform it into some d-dimensional vector. So this generator is what inducing a distribution on this space x, making that logic. Now this induced distribution is what I want to make sure that this induced distribution is same as this distribution, because this data is coming from some distribution, right? And this is my induced distribution. So I want to choose this function appropriately such that by the right choice of this function, the induced distribution will become same as this distribution. But how do I know that whatever is my current induced distribution, is it same as this distribution or not? That task is being done by this guy actually. This is called critique or adversary or discriminator, whatever you want to call. What it does, it takes as input the data sample of the original distribution, the data sample by your induced distribution, and it outputs a number between 0 and 1. Okay, and the beauty is that whenever this number hits at half, that time you can take for granted that these two distributions have become equal. If this number is anything other than half, either more close to 0 or more close to 1, the more it is away from the half, then which means that these two distributions are very different. This is the indirect signal I am giving you. You remember that originally we started that in the cloud there is a distribution PD hidden, from which this data is being generated, which I will never get to touch and feel and see, right? So if I don't get some distribution to touch, feel and see, how can I even know that these distributions are same? And that is the magic here actually. This is what is done by this discriminator. So this discriminator will start becoming more and more accurate if you give him more and more sample from both the distribution. If you give him less and less sample, it will still tell you the similarity or the dissimilarity between these two distributions, but that estimate will not be that accurate actually. Make sense? So this is the idea behind it. It has two components. One is called data generator, another is called adversary, critique or discriminator. One guy, what it does, it just takes the simple random variable, like so analogy between z here is same as the x there in that on the board what I wrote. On the board what I wrote x is same as z here. On board whatever I wrote y, that is same as x tilde here. You can think of it this way. It's just that these z's are one dimensional quantity and these x tildes are the same dimensional quantity as this original x. And we know original x are what? They are the vectored representation of images. If image is what you are trying to generate actually. It could have been text also, but then that requires a little bit of a different discussion. I'm not going to go into that in today's talk, right? So now let's try to understand what goes inside each of these boxes actually, and then how do you find the design of these two boxes, right? Any questions so far before I proceed? Just passing this thing. Okay. So if that is the case, then what I can do is, let me go to the next slide. Yes. Yeah. So this green box, how it looks like from inside, this is a neural network. I don't know how many of you are familiar with neural network. Neural network is nothing but, a feed forward neural network is nothing but a function actually. You can think of it this way. Here what happens, each edge is, this is like a directed graph, okay. So input quantity, this Z, you put at this node, okay. Then this quantity flow across all these edges, okay. Every edge had some weight, and these weights are what? Unknown. You have to decide the weights, that is called parameter of the function. So when you, so this green box which is a function, this is the detail of this function, this is how this function looks like. The input Z, you place this input here and let this input travel across each of the edge, and across each of the edge this input gets multiplied with the corresponding edge weight actually. Make sense? Now at each of the downstream node, for example look at this node, all the incoming flow will get summed up. See, at each node multiple input may be coming. From each path multiple input may be coming. It's like, you can think of it like an electric circuit, right, actually. So this current is coming and flowing along each of the edges, but then that is getting multiplied with this resistance W, right. If you want, you can think of that analogy, and then here you accumulate all the input and then apply a small nonlinear transformation on that input and then push it out actually. So you can create any complex network. This will be a very highly nonlinear function, and it's a very complex nonlinear function you can build by taking this small nonlinear function sitting at each of this node. For example, there is this, these are called activation function, like this sigmoid function, 10 hyperbolic function. There are small function which what they do, you give any number between minus infinity to plus infinity, they will give you back some number between 0 to 1, right. They are like S-shaped kind of a function, like this S-shaped function, that is called sigmoid function. Similarly, there is this thing called 10 hyperbolic function, right. So I can just draw for your benefit. So for example, if you take, this is the popular function which is called sigmoid function, this is y and this is x, and this quantity is 1 and this is 0, this is half. So the function goes something like this actually, right. So this is called this is called sigmoid function, okay. Fine. So in this sigmoid function, if you give a value of x, so this looks typically like this, 1 upon 1 plus e power minus x, okay, right. So you can verify if x is plus infinity, right, what will be this value? This will be 0, so this will be 1. If x is minus infinity, this value will be infinity, so this whole value will be 0, correct. And if x is 0, this value is 1, so this value will be half, okay. So this is the form of this function, this is called sigmoid function. Another function is called 10 hyperbolic function, right. So you should try that, I mean, let me not tell everything here. So this is called 10 hyperbolic function, so this is x, and this will also do a similar job, okay, 10hx, all right. So like that there are many actually, that's not the focus here. So what I am trying to say is, on each of this node there is this kind of a nonlinear function sitting, which takes the input, applies this function and produces the output, right. So your final output will be what? See, we started with one dimensional input. Now if you look at here, I can add as many nodes as I want, right. Depending on what is the size of the vector, you can create this network actually, right. This is a very simple example, but in practice it is very different. In practice they add something called convolution layer, max pool layer, okay, and all of that. So for that you have to take a separate course on deep learning, but here that's not the focus, but essentially the spirit this is the case actually. So why I am talking all this? So this green box is some function as we discussed. You take some random variable, push it, that funnel it through this function. After that you will get some sample x tilde. Now your goal is to choose this value of parameter w1 and all of them in such a way that whatever is the induced distribution on this xi, that is identical to this distribution, right. Then you are done your goal, am I right? So how do you do that? Now let's go further. So the idea is very simple. you assign a virtual label to each of these data points. You call each of these data point coming from class 1, right? And each of these data point, you call that they are coming from class 0. You assign some virtual label, right? They are like classification problem you would have seen, right? The patient versus non-patients and things like that. So just like a classification problem, I assign a virtual label to each of these data point of 1, virtual label to each of these data point is 0. Then what next? So now let's hypothetically assume a distribution called Px, y over this space x cross 0, 1 in such a way that this Pg of x and Pd of x, what is Pd of x? This upper arm, this path, this input, those data is coming from original distribution Pd of x, which we don't know and which we want to learn about, and Pg of x is the distribution induced by this generator, suppose, right? So ideally I want Pg of x to be equal to Pd of x. So what I do is, hypothetically I induce a distribution, joint distribution Px, y, such that if I take their conditional distribution, if y, because I have added this virtual label y equal to 0, so if I condition on y equal to 0, then obviously this P of x is what I am calling Pg of x, it's by definition, right? And if virtually I am assigning label to 1 to each of these data point, so if I condition on 1, then this distribution is what I am calling as Pd of x. And what I want these two to be equal. I want to design this box in such a way that these two distributions becomes equal. That's the problem. Are you with me so far? If any of you are lost, please ask the question. I can bring you back on the track. Any doubt? Okay. If this is not a problem, then let's try to do little algebra. We take the ratio of these two functions. Okay. So numerator divided by denominator, I just, very simple, I took these two equations and computed this ratio. So left hand side equal to right hand side because of these two equations. As simple as this. Yeah. Y is this virtual label. So this label is what I am calling as y. So with each of these data point, I also extra variable called y, which I call as a class label. And I gave that value to 1 for each of the data point which are coming from my true images, and these are called generated images. So each of the generated image I tag a label called y, and that value I assign it to 0, just so that I know that which is a generated image and which is the true image, correct? So now what happens is if I look at these two ratios, now I apply simple Bayes formula. All of you know Bayes theorem. If you apply Bayes theorem, you will get this. Let me know if somebody disagree with this formula of applying the Bayes theorem actually, right? What I have done here, I mean, you write down the, the flipped way of the Bayes theorem, and you will get this. I mean, trust me actually, right? Very straightforward. Now, what is Py equal to 1 and Py equal to 0? This is the probability that how many images have sample 1 and how many images have sample 0, which essentially mean that what is the fraction of the images, what is the probability that if I take any image which are coming as in this red box, suppose, what is the probability that that image is real image and that image is a fake image, right? If I make these two set of images equal size, equal number of images, I can always make pi to be half, right? And if I make pi to be half, this ratio becomes 1 and this disappears. That's easy, that's in my hand actually. If we can somehow ensure that pi equal to half, then what happens? Then Pg of x divided by Pd of x becomes equal to this, and if you just rearrange the terms, you get P of y equal to 1 conditioned on x is equal to this quantity. Now let's spend a minute. What is the meaning of this quantity actually, right? Let me just pause a minute, stare at these equations and just see first of all, are you not agreeing with any of this step first before we get into the purpose of all this calculation? Okay. So what is the purpose? So the purpose of the whole exercise for me is I want to choose this functional parameter inside this green box so that these two distributions become equal. But I do not know PD. I don't have closed form of this expression of PD. Neither do I have the closed form expression of PG. PG is just an induced distribution, although in some cases you can calculate it because you know the distribution of Z, you know this functional form, you can calculate it. but it's horribly complex actually. You cannot write a closed form expression for all practical purposes, right? For all practical purposes, it is as good as you don't have the closed form expression for PG, and you don't have anyway closed form expression for PD. So there is no way for you to know whether this ratio is equal to 1 or not. See, if they are equal, if these two probability distributions are equal, then this ratio should be 1 for any x. Then only you can say that you have learned that distribution. Am I right? But how do you know that this ratio is 1? Because neither you know PG of x nor you know PD of x. So this ratio to be 1, you can see now in this equation, whenever this ratio is 1, this quantity becomes half. And what is this quantity? This quantity says, given an image x, if I can guess its label right, that whether it's a fake image or whether it is a genuine image, if that probability is equal to half, which means then my PG and PX has become equal. What does it mean? Think of this as like a thief and a corpse. Think of that this data generator is like thief who is trying to produce the fake currency. Okay? Then these are the genuine currency. The goal of thief is what? They want to produce the fake currency look as real as possible. But these are the cops who wants to discriminate between the fake currency and the real currency, right? So when you will consider the thief have succeeded, when the fake currency is produced as equal as real, and when will that happen? When cops cannot catch them, when cop cannot even discriminate whether it's a fake currency or a real currency, right? In that case, which means what? Which means they perfected the art of generating fake currency. Think of it this way, right? That's what precisely I am trying to tell. If your PG of x, which is the probability distribution of the fake currency generation, PD of x is the probability distribution of the genuine currency, the moment they become half, this P of y given one condition on x, which is the probability which cop will learn, that becomes equal to half, right? Is it making sense? So in essentially what we try to do inside this red box, we train this red box in such a way that this red box can identify what is the probability given an x, given an image, it can tell me what is the probability that this image is a genuine image or a fake image. I want to train this red box accordingly and in a best possible manner. This box should be the best possible box to discriminate between the real and fake. For any given design of green, I want to train this red box such that it can discriminate between the real and the fake. And then I will revise this green box again. I will improve the green box. Again I will retrain the red box. It's like thief and cop game is going on between them actually. First thieves are improving themselves, then cop is trying to improve themselves, again thieves are trying to improve, so it's a game going on between these two. Can you see that? Chicken and egg, like cat and rat, mouse, like game is going on, race is going on between them. So what happens is this, so let's move on. So, okay. So how does this network look like? What is this network? This red network, which is called critique or adversary, this takes an image as input, okay? And as I told you that this gives a signal 0 to 1 number, which is nothing but the probability what it thinks that this image is a genuine image or a fake image, okay? So y equal to 1 means it is a genuine image, y equal to 0 means it is a fake image. So how does this network look like? It like ulta of the previous network, okay? There one real number was input and it was generating a vector. Here vector is input and what it is generating is a one number, right? It's just the matter of arranging the neural net actually, okay? You can always arrange this neural network and these Vij's are the weight vector for this network. Like Wij were the weight vector for the previous function, these Vij's are the weight vector for this red network actually. So what happens for some assignment of this Wij, this will be a function. What it does? It will take an image as the input and give you one score output. It all depends on how you choose the value of Vij's, that's all, right? By an appropriate choice of values of Wij, you can make it classify between these two currencies as accurately as possible, right? But once if this guy is so smart that he is capable of generating the currency which are looking almost like genuine, then no matter how hard the red network tries, even the best possible effort will not be able to get him more than 50% confidence, right? He will say that, okay, given any image, he will say, I am 50% confident that it is genuine, or 50% confident with probability 50% I can say it is a fake. At that point in time, you will understand that this green box has now learned the distribution. Now you can take all these images and use them as a substitute. Like in the very original picture I showed you, right? That last column of the hand generated images, at that time, whatever images is being generated by green box, they are analogous to that last column images or those bedroom images which I showed you in the previous slide. So now I think important point, maybe next few slides, I know it is becoming little heavy for some of you, but just bear with me for 2 more minutes. Okay. So, so how do we do all this actually, and where does this min-max comes into the picture now, right? All of these things which we talked about, right? So see, theta g is called as the parameter of this network. We talked, right, that big green network. Theta g is the set of all those edge weights put together, and I call that as a network weights. That is called as a network parameter for the generator, theta g. And theta d is same network parameter for the discriminator, that red colored graph I showed you, right? And the edge weights of that red colored graph, that is called as the parameter of the red network, and that we denote by theta d. So what we want to do is, let's say Q is the distribution used by this red network. First thing we want to do is this Q distribution is equal to this previous distribution, the equation which we wrote, right? So here we had written, you remember this calculation we did? What is this distribution, this equation? This equation tells that for certain choice of theta g, for certain choice of theta g, this conditional probability is given by this expression. But where will you get this conditional probability model? You don't have this model with you. See, you don't have PG, you don't have PD, you don't know these two functions, so you don't know this function also. This is just a relationship. But who will give me these functions? Neither I have this data function, which is from which data is coming, nor do I have this PG function, which is the induced probability distribution. I don't have these two functions. Even on this, in this equation right hand side, these two quantities are unknown. They are there, they exist, but I don't know them. If I don't know, which means I don't know left hand side actually, right? So this red box is essentially, we build a model for this actually. We approximate this left side. So in order to approximate this PD, see now this is the 2 level actually. We wanted to learn this PD. In order to approximate PD, we approximated via PG, right? Hoping that PG will be equal to PD. Now in order to do this, because I don't know them, then I have to approximate this quantity, conditional probability. And this is what I will do with this red box. Okay? And how it happens? This is how it happens. So in this box, this is the network. This output is a function which, given any value of x, it will give you one score. And that score is between 0 and 1, and we treat that as a probability with which this police thinks that this image x is real image. That's my assumption. And I treat this as a model for this left hand side, right? Okay?